Welcome to our comprehensive guide on IUPAC nomenclature. If you've ever wondered how chemists around the world agree on the names of complex organic compounds, you're in the right place. The International Union of Pure and Applied Chemistry, or IUPAC, has developed a systematic method for naming chemical substances, ensuring clarity and consistency in scientific communication. In this video, we'll break down the rules, walk through practical examples, and help you master the art of naming organic molecules. Let's begin by understanding why a standardized naming system is so important in chemistry. Imagine a world where every chemist used a different name for the same compound. Confusion would be inevitable and scientific progress would slow down. That's why IUPAC nomenclature is crucial. It provides a universal language for chemists everywhere. Whether you're reading a research paper from another country or collaborating with international colleagues, IUPAC names ensure everyone is on the same page. This standardization is especially important as chemistry becomes more global and interconnected. Its core IUPAC nomenclature is about assigning unique systematic names to chemical compounds. The process involves identifying the main structure, determining the longest carbon chain, and then naming substituents and functional groups according to specific rules. By following these steps, chemists can construct names that precisely describe the structure of a molecule. In the next scenes, we'll break down each part of the naming process, starting with the parent chain. Parent chain is the longest continuous chain of carbon atoms in a molecule. This chain forms the backbone of the compound's name. If there are two or more chains of equal length, the chain with the most substituents is chosen as the parent. Identifying the correct parent chain is the first and most crucial step in IUPAC nomenclature, as it determines the base name and numbering for the entire molecule. Once the parent chain is identified, the next step is to number the carbon atoms. Numbering starts from the end nearest to the first substituent or functional group, ensuring the lowest possible numbers for these groups. This step is essential for accurately describing the positions of substituents and functional groups within the molecule. Proper numbering avoids ambiguity and ensures the name reflects the actual structure. Substituents are groups of atoms attached to the parent chain but not part of it. Common substituents include alkyl groups like methyl or ethyl. Each substituent is named and its position on the parent chain is indicated by a number. When multiple identical substituents are present, prefixes like di, tri, or tetra are used. Listing substituents in alphabetical order is also a key rule in IUPAC nomenclature. Functional groups are specific groups of atoms that impart characteristic chemical properties to a molecule. In IUPAC nomenclature, certain functional groups have priority over others when naming compounds. The group with the highest priority determines the suffix of the compound's name, while others are treated as substituents. Understanding the order of precedence is crucial for accurate naming. Some of the most common functional groups include alcohols, aldehydes, ketones, carboxylic acids, and amines. Each group has its own suffix or prefix in IUPAC nomenclature. For example, alcohols use the suffix -ol, while carboxylic acids use OIC acid. Recognizing these groups and knowing their naming conventions is essential for constructing correct IUPAC names. IUPAC nomenclature uses specific suffixes and prefixes to indicate the presence of functional groups and substituents. The main functional group is indicated by a suffix, while other groups are named as prefixes. For example, a compound with both an alcohol and a methyl group would use "-ol" as the suffix and "methyl" as a prefix. This system allows chemists to convey detailed structural information in a single name. Alkanes are the simplest class of organic compounds, consisting only of carbon and hydrogen atoms connected by single bonds. Their names end with the suffix -ane. The base name reflects the number of carbon atoms in the longest chain, such as methane 1 carbon, ethane 2 carbons, propane 3 carbons, and so on. Understanding alkane nomenclature is the foundation for naming more complex molecules. Alkyl groups are derived from alkanes by removing one hydrogen atom. They are named by replacing the -ane ending with -il. For example, methane becomes methyl and ethane becomes ethyl. Alkyl groups act as substituents when attached to the parent chain and their positions are indicated by numbers. Recognizing alkyl groups is essential for accurate IUPAC naming. Alkenes and alkanes are hydrocarbons that contain double and triple bonds, respectively. Alkenes use the suffix -ene while alkanes use -un. The position of the double or triple bond is indicated by the lowest possible number. For example, but 2-ene has a double bond starting at the second carbon. These rules help specify the exact structure of unsaturated hydrocarbons. Cycloalkanes are ring-shaped hydrocarbons with only single bonds. Their names begin with the prefix cyclo followed by the alkane name. For example, cyclohexane is a 6-carbon ring. Numbering in cycloalkanes starts at a substituent or functional group and proceeds to give the lowest numbers to all substituents. This ensures clarity in naming ring structures. Branch chains occur when side chains or substituents are attached to the main carbon chain. The longest continuous chain is still considered the parent chain and branches are named as alkyl groups. Their positions are indicated by numbers and multiple branches are listed in alphabetical order. This approach ensures that even complex molecules can be named systematically. When a molecule contains more than one double or triple bond, the suffixes diene, triene, or diene are used. The positions of each bond are indicated by numbers. For example, hex-13-diene has double bonds at the first and third carbons. This rule allows chemists to describe molecules with multiple points of unsaturation accurately. Alcohols are organic compounds containing a hydroxyl OH group. In IUPAC nomenclature, the suffix -ol is added to the parent chain and the position of the hydroxyl group is indicated by a number. For example, butane-2-ol has the O group on the second carbon. If multiple hydroxyl groups are present, prefixes like diol or triol are used. Aldehydes and ketones are carbonyl-containing compounds. Aldehydes use the suffix al and the carbonyl group is always at the end of the chain, so no number is needed. Ketones use the suffix 1 and the position of the carbonyl group is indicated by a number. For example, pentan 2,1 has the carbonyl group on the second carbon. These rules help distinguish between similar compounds. Carboxylic acids contain the COOH group and use the suffix OIC acid. The carboxyl group is always at the end of the parent chain, so numbering starts from this carbon. For example, ethanoic acid is a 2-carbon acid. If there are additional substituents, their positions are indicated as usual. Carboxylic acids are a key functional group in organic chemistry. Esters are derived from carboxylic acids and alcohols. Their names consist of 2 parts, the alkyl group from the alcohol and the acid part with the suffix -ote. For example, methyl ethanoate is formed from methanol and ethanoic acid. The alkyl group is named first, followed by the acid-derived name. This naming convention helps identify the components of the ester. Amines are compounds containing a nitrogen atom attached to one or more alkyl groups. Primary amines use the suffix amine, and the position of the amino group is indicated by a number. For example, butane 1-amine has the amino group on the first carbon. Secondary and tertiary amines are named by listing the alkyl groups attached to the nitrogen. Ethers are compounds with an oxygen atom connecting 2 alkyl or aryl groups. In IUPAC nomenclature, ethers are named as alkoxy derivatives of alkanes. The shorter alkyl group is named as an alkoxy substituent, such as methoxy or ethoxy, and its position is indicated by a number. For example, methoxyethane has a methoxy group attached to ethane. Halides are organic compounds containing halogen atoms like fluorine, chlorine, bromine, or iodine. In IUPAC nomenclature, halides are named as substituents using prefixes such as fluoro, chloro, bromo, or iodo. Their positions are indicated by numbers, and they are listed in alphabetical order with other substituents. This approach ensures clarity in naming halogenated compounds. Nitriles are compounds containing the CN group. In IUPAC nomenclature, the suffix nitrile is added to the parent chain. The carbon of the nitrile group is included in the parent chain and numbering starts from this carbon. For example, ethanitrile is a 2-carbon nitrile. This naming convention helps identify the presence and position of the nitrile group. Amides are derivatives of carboxylic acids where the O group is replaced by an NH2 group. The suffix amide is used and the carbonyl carbon is always at position 1. For example, ethanamide is a 2-carbon amide. If there are substituents on the nitrogen, they are named as N-substituents. This systematic approach ensures clarity in naming amides. Anhydrides are compounds derived from 2 carboxylic acids. Their names are formed by combining the names of the parent acids, followed by the word anhydride. For example, ethanoic anhydride is derived from 2 molecules of ethanoic acid. This naming convention helps chemists quickly identify the structure and origin of anhydrides. Acid chlorides are derivatives of carboxylic acids where the O group is replaced by a chlorine atom. The suffix ol chloride is used in IUPAC nomenclature. For example, ethanol chloride is derived from ethanoic acid. This systematic naming helps chemists identify the functional group and its position within the molecule. Nitro compounds contain the NO2 group. In IUPAC nomenclature, the prefix nitro is used and its position is indicated by a number. For example, 2-nitrotoluene has a nitro group on the second carbon of toluene. This naming convention ensures that the presence and position of the nitro group are clearly communicated. Sulfonic acids contain the SO3H group and use the suffix sulfonic acid in IUPAC nomenclature. The sulfonic acid group is always at the end of the parent chain and numbering starts from this group. For example, benzenesulfonic acid is a common sulfonic acid. This systematic approach ensures clarity in naming these compounds. Aromatic compounds such as benzene and its derivatives have unique naming conventions. Substituents on the benzene ring are indicated by numbers or by using ortho, meta, and para prefixes for disubstituted benzenes. For example, 1,3-dimethylbenzene or metaxylene. Understanding these conventions is essential for naming aromatic compounds accurately. When a molecule contains more than one functional group, the group with the highest priority determines the suffix while others are named as prefixes. The order of precedence is established by IUPAC rules. For example, a compound with both a carboxylic acid and an alcohol group is named as a carboxylic acid, with the alcohol as a hydroxy substituent. This ensures systematic and unambiguous naming. Stereochemistry refers to the spatial arrangement of atoms in a molecule. IUPAC nomenclature uses prefixes like R, S, E, and Z to indicate stereochemistry. These prefixes are placed before the compound's name and provide information about the configuration of chiral centers or double bonds. Correctly indicating stereochemistry is essential for distinguishing between different isomers. Cis-trans isomerism occurs in alkenes and cyclic compounds where substituents can be on the same or opposite sides. The prefixes cis and trans are used to indicate these arrangements. For example, cis-2-butene and trans-2-butene are different compounds with distinct properties. Properly naming cis-trans isomers is important for clear communication in organic chemistry. Polymers are large molecules made from repeating units called monomers. In IUPAC nomenclature, the prefix poly is used, followed by the name of the monomer in parentheses. For example, polyethylene is the polymer made from ethylene monomers. This naming system helps chemists identify the building blocks of polymers and their structures. Even experienced chemists can make mistakes in IUPAC nomenclature. Common pitfalls include incorrect numbering, forgetting to list substituents alphabetically, or misidentifying the parent chain. Double-checking each step and following the rules carefully can help avoid these errors. Practice and attention to detail are key to mastering IUPAC naming. Let's put the rules into practice with a simple example. Consider a molecule with 4 carbon atoms in a straight chain and no substituents. The longest chain is 4 carbons, so the parent name is butane. There are no branches or functional groups, so the IUPAC name is simply butane. This example shows how straightforward naming can be when you follow the steps. Now let's try a branched alkane. Suppose you have a 5-carbon chain with a methyl group attached to the second carbon. The parent chain is pentane and the substituent is a methyl group at position 2. The correct IUPAC name is 2-methylpenane. This example demonstrates how to apply the rules for naming branched alkanes. Consider a molecule with 3 carbon atoms and a double bond between the first and second carbons. The parent chain is propane and the double bond starts at carbon 1. The correct IUPAC name is prop-1-ene. This example shows how to indicate the position of a double bond in an alkene. Let's name a molecule with 3 carbon atoms and a hydroxyl group on the second carbon. The parent chain is propane and the O group is at position 2. The correct IUPAC name is propan-2-ol. This example illustrates how to name alcohols by indicating the position of the hydroxyl group. Consider a molecule with 2 carbon atoms and a carboxyl group at the end. The parent chain is ethane and the carboxyl group makes it ethanoic acid. This example shows how the presence of a carboxyl group determines the suffix and numbering in IUPAC nomenclature. Let's try naming an ester formed from methanol and propanoic acid. The alkyl group from methanol is methyl and the acid part is propanoate. The correct IUPAC name is methylpropanoate. This example demonstrates how to combine the names of the alcohol and acid components in ester nomenclature. Consider a molecule with 3 carbon atoms and an amino group on the first carbon. The parent chain is propane and the amino group is at position 1. The correct IUPAC name is propan-1-amine. This example shows how to name amines by indicating the position of the amino group. Let's name a molecule with 5 carbon atoms and a carbonyl group on the third carbon. The parent chain is pentane and the carbonyl group is at position 3. The correct IUPAC name is pentan-3,1. This example illustrates how to name ketones by indicating the position of the carbonyl group. Consider a molecule with 4 carbon atoms and a chlorine atom on the second carbon. The parent chain is butane and the substituent is chloro at position 2. The correct IUPAC name is 2-chlorobutane. This example demonstrates how to name halogenated compounds using prefixes and position numbers. Let's name a molecule with 3 carbon atoms and a nitrile group at the end. The parent chain is propane and the nitrile group is included as the suffix. The correct IUPAC name is propanenitrile. This example shows how to name nitriles by including the nitrile carbon in the parent chain. Congratulations on reaching the end of our IUPAC nomenclature guide. We've covered the essential rules, functional groups, and common examples to help you master organic chemistry naming. Remember, practice is key. Work through examples, double-check your steps, and refer to IUPAC rules when in doubt. With time and experience, you'll find that systematic naming becomes second nature. Thanks for watching and keep exploring the fascinating world of chemistry.